one-sided limits. So still a little bit here going on with limits, but continuity is kind of a new idea for us. So we'll probably start with that and then work our way toward the one-sided limits toward the end. Okay, continuity. Hello there, Hannah. Thank you. All right, this is for you, Avery. Maybe just after the lesson, if you want to put down this, you can. Let me give you a few conditions that have to be met in order for a function to be continuous. Continuity, continuous, it's all kind of together here. And so it says continuity at a point. Continuity at a point. And it says a function f is continuous at x equals c. A function f is continuous at x equals c if the following three conditions are met. A function f is continuous at x equals c if the following three conditions are met. And I'm going to list those three conditions now. These are very important. We have to know what these are. First of all, f of c is defined. Okay, that's one of our conditions. For it to be continuous at this value of x, whatever it is, that c, it has to be defined there. And so, in particular, that means there can't be a hole. If there's a hole at x equals c, it would not be defined. So no holes. Also, no like vertical asymptotes, anything like that. That would make it not defined at that value. So f of c has to be defined. Okay, I'll show you some examples of all of this here in a second. But let's go ahead and just get what the conditions are first. So, condition 2, the limit as x approaches c of f of x exists. So the function has to be defined at c, but also the limit as x approaches c has to exist. Again, once we go through our examples, all of that stuff should make a little bit more sense. But here comes example 3, condition 3, and it says the limit as x approaches c, of f of x equals f of c. And that is actually kind of putting those two other conditions together. This limit as x approaches c of f of x comes from condition 2 right there. Whatever that limit is, it has to equal whatever the function is at c. So whatever you get from condition 1 and condition 2, those should just be some kind of numbers. That should be equal to each other for that third condition. Again, all of that right now is a little blurry, I'm sure. We'll go ahead and start our examples. And this is what the directions say. It says, discuss the continuity of each graph. Discuss the continuity of each graph. And I will be kind of picky about how you discuss it. You're going to have to be particular about, which condition fails, or maybe it's just continuous everywhere. But there's going to be something about those conditions that we have to talk about. Now, there's several graphs that we're doing in the notes today. So to save time, instead of having you guys recopy them every time in your notes, I've made copies for you. Yep. You can still kind of write your answers and do your work and stuff in your notes, whatever you're writing on. Yep. But this, again, is just to kind of look at so we don't have to spend time, yes, recopying everything. Now, don't work ahead. I know they're all on there, but don't work ahead because, again, this is brand new. And actually, I'm going to change the directions toward the end, so you'll want to make sure that you just kind of follow along. But here is the first one. And, I mean, it might even be better if you look up here for the notes. Again, this paper that I gave you right now is just to kind of put in your notes later so you remember what was going on. Okay, discuss the continuity of this graph. First of all, I'm always going to look for problem areas, holes, asymptotes, breaks in the graph. Those are all problem areas for continuity. So if you look at these X's that this graph is taking on, I mean, everything over here is fine. It's just a line. Everything over there is fine. But the one X value that I'm concerned about, the problem area, is where X equals 2. Now, let's think about our three conditions. Condition 1, and if you're going back and reading the condition, the C in that condition for us right now is 2, because that is the problem area. That's where we're focused right now. So if you look at condition 1, it says that f of 2 is defined. On this graph, is f of 2 defined? Could you say what f of 2 was? You can find the limit. Condition 2 would be fine. You could find the limit as x approaches 2, but can you say what f of 2 is? No, because there's a hole there. And so, according to our conditions, first condition on that list is the one that fails. F of 2 is not defined because there's a hole there. And so here's what I would say, and again, you have to be specific. You have to use the X value and tell specifically which condition is not working. I said discontinuous, or you could say not continuous, at X equals 2 because f of 2 is not defined. Don't leave it as f of c. I know that's how they wrote it in the condition, but now that you have a graph to look at, find that x value in particular that's not working. Okay, f of 2 is not defined. That is the condition that fails. So that is how we would discuss the continuity of that graph. Okay, I'm going to keep going here. So again, make sure that you write that down. You got to be specific. Can't just say not continuous at 2. You really have to say why. Which one of those conditions isn't working. Okay, now you've got this in front of you again, but it might even be better to kind of look at it up here. It's a little bit bigger. I am going to run through, or first of all, I'm going to look at my problem areas. I'm going to look for any X's where weird things are happening. All these X's are fine right here until I get to where X is negative 2. Same on this side. Everything's fine and dandy, but the graph gets weird at X equals negative 2. There's a break in your graph. So again, that is what I'm going to look at on my conditions. I'm going to look right here where X is negative 2. Now condition 1 says that f of negative 2 has to be defined. Why don't I just kind of run through this a little bit down here. You can write this down if you want. F of negative 2 has to be defined. If you look right here on your graph, what would you say f of negative 2 is? 1. It's what the function equals when x equals negative 2. We're not talking limits for the first condition. We're just talking about the function. F of 2 would be 1. Now, for condition 2, I'm looking at the limit as x approaches negative 2 of f of x. The second condition says that this limit has to exist. So what would you say about the limit as x approaches negative 2? Does not exist because it's going toward two different y values. And so condition 2 is the one that fails. I'm writing this out not really because you have to write all of this out, but because this is kind of what I'm going through in my head. F of negative 2 was fine, but the limit as x approaches negative 2 does not exist. This is how I would formally discuss the continuity of that graph. I would say it's discontinuous or not continuous at x equals negative 2 because the limit as x approaches negative 2 does not exist. It's not enough just to say that it's not continuous at negative 2. You got to say specifically which one of those conditions did not work. Okay? If you can't find condition 1, if condition 1 fails, then you can't even do condition 3. And same here, if condition 2 fails, you can't even find the limit, then you can't go on to condition 3 because it doesn't even exist. Okay, stop me if you have questions. I'm going to keep on rolling here. This is number 3. And, okay, there's a line. I've got a hole right here. Right under it, though, there's a point. So again, let me kind of run through what I'm thinking in my head for each condition. You don't have to write all this down every time, but condition 1, and again, I'm looking for problem areas. The problem x value is right here where x is 4. So for condition 1, we have to make sure that f of 4 is defined. What would you say f of 4 is? 1. That is what the function equals when x equals 1, so that's good. Now, condition 2 says the limit as x approaches 4 of your function, we don't really know what the function is, but the limit as x approaches 4 has to exist. As you get closer and closer to where x is 4, what would you say the limit is? 3. It's approaching the y value of 3, so condition 2 is actually fine. Then I move on to condition 3, which says, I'm going to squeeze this in, the limit as x approaches 4 has to equal f of 4. Again, I know to use the x value of 4 because that is the problem area on my graph. That's where things get weird. So I'm checking, does the limit as x approaches 4 equal f of 4? And you can actually get those numbers right here. I'm going to just draw an arrow because I ran out of room. But limit as x approaches 4 was 3. And f of 4 was 1. 3 obviously does not equal 1. Our limit as x approaches 4 does not equal f of 4. That is the condition that fails. So I'm going to have to say that it's discontinuous at x equals 4 because, we have to explain why, because the limit as x approaches 4 of f of x, whatever that function is, does not equal f of 4. F of 4 was 1, but the limit as x approached 4 was 3. Again, all of this stuff right here is just stuff that I'm thinking about. You don't actually have to write all that, but you do need to have that part down. Any questions so far? Checking these conditions. We're going to do one more of these, and then I'm going to change the directions for the last few graphs that you have. We'll talk about one-sided limits after this one. But here's number 4. Okay, it's just a line. There's no holes. There's no asymptotes. There's no weird breaks in the graph. If you don't have any of those things going on, if there's no problem areas anywhere, this line is just going to keep going on forever and ever, then we would just say it's continuous everywhere. You can't even really do the 3 conditions because you don't have an x value that's a problem. Okay, I guess you could do the 3 conditions, but it would check out no matter what x value you are looking at. So continuous everywhere. Hello there. This is the first part of 1-4 if you want to just jump in with us. Okay, any questions about continuity? Continuity. We're going to keep using this stuff here in a little bit. Before we switch over to the next few graphs, we do have a little bit to talk about as far as one-sided limits go. And so this would be something I want to make sure gets in my notes. One-sided limits. Normally, when we find a limit from a graph, we come in from both sides. That was always the rule. Well, there's such a thing as one-sided limits, which is where you're only coming in from one side. So there's some notation up here that you're going to want to copy down. And it has the limit as x approaches c. C can be anything, but notice there's a little plus sign right after the c. It's almost up kind of like where an exponent would be. If you have a plus sign with your value, then you are finding the limit as x approaches c from the right. The plus sign indicates you're coming in from the right. Okay, the limit as x approaches c from the right. Now, I'll go ahead and just put the other one up here because it's just the opposite. Now, it has the limit as x approaches c, but then up where like an exponent would be, it has a minus sign. That indicates that you're finding the limit as x approaches c from the left. The minus sign means left. Okay, so when you do this on a graph, you don't have to use 2 fingers anymore coming in toward an x value. You only have to use 1. If it's a plus, coming in from the right. If it's a minus, you're coming in from the left, and you're still trying to figure out what y value you're approaching as you do that. Okay, let's go ahead here, and I'm going to give you some new directions for the last few. You already have the graphs in front of you, but this is what we have to do. Use the graph to determine each limit. Use the graph to determine each limit and discuss the continuity of the graph. Brooklyn, I'll print those notes out here in a little bit, but continuity is something we talked about at the beginning. Use the graph to determine each limit and discuss the continuity of the graph. So we'll still have to check those three conditions once we find some limits. Okay, graph is in front of you, but here is what we have to find for part A. This is the part that you'll want to put somewhere. You can put it on the graph paper or on the paper that you're just writing on. For part A, we have to find the limit as x approaches 0 from the right. You're not going to the right, you're coming in from the right. That's what the plus sign tells me. So this is where x is 0. That's the x value that I'm approaching, but I'm only coming in towards 0 from the right. So as you get closer and closer to where x is 0 from the right, what y value are you approaching? 4. So my answer for part A would be 4. Now part B says that we need to approach 0 from the left. It's the limit as x approaches 0 from the left. Caitlin?
How did you get 0?
This is given to you.
Oh.
Yes, that's the problem. That's what you're supposed to find. So it didn't have to be 0. It could have been a different x value. Yes. Now, coming in from the left toward where x is 0, I'm getting closer and closer to that. What y value am I getting closer and closer to? 4. So let's go ahead and say part B would also be 4. Now, something that you'll want to pick up on is, here's part C. If the limit as x approaches a number from the right equals the limit as x approaches 0 from the left, if you get back the same number from part A and part B, then when you do part C and there's no plus or minus, that means you have to go back to coming in from both sides. I'm still approaching the y value of 4. So it's not always going to be all the same. It just is on this graph. But again, if the limit from the right equals the limit from the left, then part C, the limit from both sides, would still have to be that number. All right, now don't forget to discuss the continuity. If you look at this graph, are there any x's that concern you? Holes, asymptotes, breaks? No. So I would say for that part that it's just continuous everywhere. That's the last part of our directions. Okie doke. I'll keep going here. You have the graph for number 6 already, but I'll give you the parts here. They should probably be about the same. Part A, we want to find the limit as x approaches 0 from the right. The limit as x approaches 0 from the right. This is a very common graph when we're dealing with one-sided limits because there's like 2 different things going on. Now, if I have to come in from the right, then I want to ride along the part of the graph on the right. I'm not even really going to use this part of the graph for part A because I'm only coming in toward 0 from the right. So what y value am I approaching as x approaches 0? Yes, from the right, the y value that I'm approaching is positive 1. It doesn't matter that there's a hole there. Remember, for limits, you can still approach a number even if there's a hole there. Now, when I go to do part B, I want the limit as x approaches 0 from the left. So as you get closer to where x is 0 from the left, what y value are you approaching? -1. You're actually right at -1 the whole way. Now, part C, I need to figure out, in general, the limit as x approaches 0. If there's no plus or minus, then you're coming in from both sides. What would you say about the limit as x approaches 0 from both sides? Does not exist. If your answers from A and B are different, then the limit is not going to exist for part C. Now, we do still have to discuss continuity, and there's actually 2 different conditions that fail here, so there's probably 2 different things you could say. But if you go through the list, condition 1, and remember the x value that we're concerned about here is 0. Condition 1 says that f of 0 has to be defined. Is the function defined where x is 0? No, there's just holes everywhere. So that's what I said. Discontinuous at x equals 0 because f of 0 is not defined. Another option would be that it's discontinuous at x equals 0 because the limit as x approaches 0 does not exist. You can't even really do condition 3 on something like this, but again, you could address the first condition or the second with this type of graph. Okie doke. Any questions on that one? All right. Well, let's try, I guess, just one more here. Lucky number 7, last one. It kind of looks like absolute value almost, upside down though, with a hole, and then a random point up there at 1, 4. Well, part A, and you could already kind of figure out what x value is the problem on this graph. We're mainly focused at where x is 1. So part A, I need the limit as x approaches 1, this is where x is 1, from the right. So what y value am I approaching as x gets closer to 1 from the right? 2. It's getting closer to where y is 2. What about as I approach x equals 1 from the left? 2. And I mean, you can go ahead and do both of your fingers if you want for part C, but like I said earlier, if these 2 answers are the same, then the limit from both sides would also have to be that number. So, answer to part C, the limit as x approaches 1 is just 2. Okay, now we have 3 conditions. And it's not continuous everywhere, I'll just tell you that much. Which condition fails, do you think? Condition 1, 2, or 3? I would say, yeah, 3. The f of 1 is defined. F of 1 is 4. But the limit as x approaches 1 is 2. So there we go, discontinuous at x equals 1 because the limit as x approaches 1 of f of x does not equal f of 1. Very good. So it's basically continuous everywhere except for that x value of 1. Okey-doke. Any questions? Continuity, one-sided limits. Okay, the assignment is just out of the book. I'm sure you'll have lots of graphs to look at here. I'll go ahead and put this up. It's C21 from page 96. What are we doing? Numbers 1 through 6 and then 29 to 32.